Hello, it's Keith here, and this is lesson 12 of the so-called ChibiFighter programming tutorials. Today we're looking at the ZX Next version of the code, and I'm stuck on the floor and I can't get up. That's because I've got the key set to the wrong thing. So we're going to be looking at this version of the game. Now what we're going to look at today is the platform-specific code of the Spectrum Next. Basically, the graphics routines and the sound routine. We're using interrupt-driven sound, and this is using my Chibi Tracks music player. This is my new music player. So we're going to be looking at the code for the Spectrum Next today. I thought this was quite interesting. Spectrum Next, I'm not generally a fan of these sort of remade consoles and things, but the Spectrum Next is one of the very few 16 color Z80 based systems that allows for direct memory access. The MSX2 has a very odd way of working with the hardware. The Sam Coupe does allow 16 colors as well, but its memory mapping for the video memory is a little bit more tricky, so the Spectrum Next is very good. We're actually using the 256 color mode today. I'm only using 16 of the colors though, because this game was ported from a 4 color game, so I haven't really got the capacity for 256 colors. Anyway, let's go over and let's take a look at the code today. Okay. So here is the code. Now what we're going to be looking at, as I say, is the parts that relate to the interrupt handler for the music, and also the parts that relate to the graphics, because that's really all there is to the platform specific code for this game. This game uses a graphics engine which I call Mintile. It's a little graphics routine that uses a tile map, which it uses to simulate sprites as well. And so all of that is actually multi-platform code, and it's just the code that draws a single strip of the tiles that's platform specific speed, and also the interrupt handling is very platform specific as well. So our program actually loads to memory address 6000 here, so that we've got the most memory possible for our game code. Now the first thing we're going to do after we've set up our palette is we are going to set up our interrupt handler. Now I'm using interrupt mode 1. I really don't like interrupt mode 2. Tends to be a necessity on the Spectrums with ROM in the low memory area, but the Spectrum Next does not require to have ROM at that area. So we're using next reg 50 in hexadecimal here. And we're going to page in a bank of memory with this bank here, and we're going to page that into the 0 to 1 FFF range. So the sole reason we're doing that is actually so we can get our interrupt handler. I mean, I guess more memory the better anyway, but the reason we needed to do that is for our interrupt handler. So we're loading memory address 38 here as the destination in hexadecimal. We're loading a jump, that C3 is a jump, to our interrupt handler into that memory address, and that is going to mean that whenever the interrupt occurs, we will jump to our interrupt handler. So that has paged in some RAM at the memory range there, and what we're actually going to do is we're going to use the 2000 to 3 FFF range for video access. So we're going to still use that video overlay of the ROM area for writing to video memory. Now, one limitation that does still rather annoyingly exist on the Spectrum Next is the way the interrupts work. On the Amstrad CPC, if you disable interrupts and an interrupt fires, it will wait until interrupts are enabled. MSX2 and the Master System do the same. Spectrum doesn't do that, and I don't believe there's a way of changing that functionality on the Next. So we're going to avoid disabling interrupts on this system. Not actually a problem because the Spectrum Next processor is so fast. That was a problem for the Sam Coupe. Spectrum Next just stupidly fast because it's a simulation of a Z80 processor. It's not 6 megahertz or anything. I think it runs at 14 or more, so it's very fast. Anyway, our interrupt handler is very straightforward. All we do is we run Chibi Tracks Play. That is my music tracker's play routine. That uses B, C, D, E, H, L, and IX and the accumulator and flags, obviously. It doesn't use shadow registers and it doesn't use IY, so we're not backing those up at all. Now, we're not using the shadow registers for BCDE and HL because other parts of the Mintile graphics routine do use that, but nothing uses the A shadow registers, so that's why I'm using those. So that's our interrupt handler. That's all there is to our sound, really. We just turn on interrupts and that will do our sound. Now, our graphics, the game, as I say, was based on a 4-color game, and I wanted to try something a bit different for this one. When I'm porting games to systems with more colors, often I have a problem that my 4-color graphics double in size when I go to 16 colors, and that can be a big problem if I'm trying to avoid multi-load. A game that works quite nicely within the 48K of the CPC with its 4 colors suddenly becomes a major problem on the Sam Coupe with its 16. So I thought, well, rather than having 16 color graphics, let's use just 4 color graphics and let's convert them to 16 in relative real time. And so what I've done is I've split the palette into 4 blocks of 4. The 16 colors are for 4 color palettes now. And so we've got some oranges for the title screen, some colors for the Chibico character, some colours for the Eureka character, that's the enemy's character in this game, and the green for the backgrounds here. So we've got those 4 palettes here, and I'm referring to those as a tint. Now, you'll see at the start of the game and in various parts of the code, we're defining a tile tint, and we're setting basically the remaining bits of the color number for the graphics. And so whatever graphic routine follows that, we'll use that. And in that case, it's going to be the title screen, but later on you'll see we're using it for things like drawing the enemy sprite or player sprite and things like that. Now, the graphics routines basically all come down to this do strip routine, but we do have a get screen pos calculation, and this is for the sprites, which are basically a miniature tile map. It's all tile map code. There is no hardware sprites. There's no clever sprite code. I've repurposed the tile map code to reduce the amount of platform-specific code. Mintile is an intentionally crude tile map. I'm working on a better one called Max Tile, which is more advanced, but as I say. So anyway, so what we're doing here is we're taking the logical coordinates for B and C, and we are converting them into a Y tile position and an X byte position here. And then what we're doing here is we are taking the Y line and we are calculating it as an offset within an 8K bank and a bank number. So here we're calculating the offset within the bank. We're then basically adding hexadecimal 2000 here because our VRAM, it goes from 2000 to 3FFF, so 2000 to 3FFF there, and so we are ORing in that bit there to set that to the minimum of 2000 there. We're then basically storing that as our VRAM destination, and then what we're doing is we're taking the top 3 bits and we're converting those to a bank number, and we're then paging that bank in using nextreg51, which will page that bank into that range there. And so by running this get screen pos routine, we are calculating the offset within the VRAM bank and paging in the VRAM bank. Now, when we move down a strip of 8 tiles, we will actually need to recalculate that potentially because we might have gone over a bank. So that is something we will need to do at other places in our code. Now, here is our do strip routine, and so what this does is it draws a single strip of the tiles. The mintile routine has the code that builds those strips into a complete tile map. Now, this routine will have passed to it a DE offset, which is the address of the pattern data in memory, a BC address, which is the tile map or miniature tile map for the sprites. The sprites are also made of tiles, you see, and we're going to draw them to the HL destination in VRAM. So basically what we're going to do here is we're going to load in the tile number. If the tile is 0, then there's nothing to do. Now the background is basically done as a tile cache with updates, and so it says update these tiles, they've changed. A 0 in that cache means there's no update needed. So in that case we're skipping over. Now you'll see here we've got some self-modifying code, and what we're doing here is we're wiping the tiles after we've read them in. We do that on the cache but not on the sprites, so that will be changed to a no op, I think it is, if we're drawing a sprite here. We're then basically multiplying the tile number by 16 here, because there's 16 bytes for our 4 color tiles. Remember, they're into 4 colors, and we're going to convert them to 256 colors for this system. We're adding that to DE, and HL is now the address of our source data. So we're popping that out here, and we're getting the tile tint, and we're loading that in B. So DE is our 4 color data. HL is our VRAM destination. And so what we're going to do is we're going to pop 2 bits out of our source data. We're loading our data, pop 2 bits out of C, and we're going to store those to the screen after ORing in our tint. So that has done 1 pixel to the screen. We then repeat that, get another 2 bits. That's the 2nd pixel, that's the 3rd pixel, and that's the 4th pixel. Now our source data is 4 colors, and that means we have 4 pixels per byte. So at this point we've exhausted our source data, so we load in a 2nd byte, and we store that in C, and then we do the same. So we're doing the next byte of source data and the second block of 4 pixels to the screen. So at this point we've done an entire 8 pixel wide strip of our sprite. We are moving back 1 tile, moving down 1 full line, because there's 256 bytes per line, because it's one byte per pixel here in 256 color mode. And then we're repeating. Now this routine is basically relying on working in whole tiles that are vertically aligned by 1 full tile. If we were going over a memory boundary, then we might need to page in new VRAM or something at that stage. So that isn't going to work so well on this routine. It's a routine that's limited to a Y jump of 8 pixels there. So that's what we're doing there. Once we've done an entire tile, we're moving back up 1 tile, because we then go across doing the remainder of the strip. and we move across the screen by one tile, and then we repeat until we've done all the tiles of that strip. Okay. Now, in the case that the tile was empty, we just skip the source data and we move across, having done nothing, and then we repeat again. So that's how we draw tiles across the screen. But sometimes our players will turn around. The background tile map can't turn around, but the players can turn around. And in that case, we need to flip the source bitmap data. And so what we've got here is the code to do that. The first bit's exactly the same. We're calculating the source bitmap data. And so what we're going to do here is we're basically going to do the same, but in this case, we're going to read in our source data here. But after each write of a byte to the screen, we're going to move left one pixel, so 1 byte. So we're drawing the bitmap data in reverse onto the screen here. So that's how we're flipping our sprite to face the other direction here. Apart from that, the code is all the same. We're doing the same shifting of 2 bits into our destination byte and writing it to the screen. And we are basically moving back up one, and we're still moving across the screen horizontally because the bitmap data of the sprite has been reversed as we go. And you can see as we're loading in our source tile numbers here, we're actually decreasing BC. So we're reading the tile map backwards and drawing them to the screen in reverse across the screen in the same way. So that's how we are drawing our character flipped around to the screen. So there we go. So that's all we've got for today. That's the Spectrum Next version of the code. So I was quite pleased with it. Spectrum Next or the Sam Coupe are my go-to systems for porting a game from the Amstrad CPC onto other systems. The MSX2 has its own quirks because of its VDP methodology. The Master System is one of my favourite systems, but it's a tile sprite based system, so it doesn't work in the same way as the CPC. If I want to sort of start bridging that gap into 16 colours and things, the Spectrum Next or the Sam Coupe are some of the easiest, and actually the Spectrum Next is the easiest because, as I say, it's got advanced memory mapping and things, so it doesn't have the same memory limitations as the Sam Coupe. So if you want to port a game to a system that's got a lot of power, Spectrum Next is the one I would probably recommend. Anyway, I hope you've enjoyed what you've seen today. As I always go to the website, download the sources, build scripts, and you can do whatever you want with them. Let's show this one for a change. I'm planning to do a new channel probably next year on programming other languages. So that's on a channel called Chibi Androids. So if you want to subscribe to that, go ahead. It won't have any content coming soon, but I need to start announcing it now, or it'll never have any viewers either. Hope you've enjoyed what you've seen today. Thanks for watching, and goodbye.